Welcome to the lesson video on dimension reduction. Dimension reduction is a process of creating a number of new features out of the original features, where the number of new features is less than the number of original features. So the way it's written here, K is the number of new features, P is the number of original features, and then K is going to be less than P. Dimension reduction can be useful for improving prediction accuracy when those K new features capture most of the information, most of the important information originally present in the original features. And one of the benefits of doing dimension reduction, less training data will be required for training when you have fewer features. It's a little bit of a reminder of how principal components work and what principal components are. We've talked about these previously in a previous lesson video. Here's an example of principal components in the advertising data set. So in this plot, we have population on the horizontal axis and advertising spending on the vertical axis in a number of cities. There's about 100 different cities shown in the purple dots. And the principal components will give us the directions of greatest variance. And so the first principal component is shown here. And the principal component vector is really specifying this linear space. It could have used the vector that's shown there or the one pointing in the opposite direction. It's equivalent as far as the principal components are concerned. Either of those would be considered the first principal component. It's more about that direction of spread in the data, not direction up and right versus down and left. And then the second principal component points in the direction that is perpendicular to the first principal component and in the greatest variance in the directions that are remaining. So we're in 2 dimensions, so there's only really one option here, but if we're in 3 dimensions, it would be a lot of different options for the second principal component. And so there's where the second principal component is for this data. And we can use principal components as a dimension reduction for linear regression by, instead of doing the linear regression on the original variables, we compute the principal components, and then we use a subset of those principal components for the regression. Typically, we try to find a subset of the principal components that captures all the important information, and that allows us to work with less training data or get better accuracy with the same training data. And so here's an example of principal components regression on the credit data set. So on the left-hand side, we have a plot of the number of components on the horizontal axis and then the standardized coefficients. So when you do principal components regression, you get standardized coefficients that tell you effectively the coefficients for the different variables. You can see the gray variables that aren't very important, and then the 3 that are important are shown in this key. And on the right-hand plot, we have number of principal components as a function on the horizontal axis, and then cross-validation mean squared error. So, for example, for 2, the first 2 principal components were used as the new feature, or the new 2 features, and then linear regression was performed using just those, and the mean squared error for that linear regression using cross-validation is this here. And you can see as we increase the principal components, we're generally decreasing the error for a while till we get to 10, and 10 is where the minimum error occurs. So in this data, the best results occur when using 10 principal components. So one of the things you can think about with principal component regression, it finds latent variables, or variables that are hidden in your data kind of behind the variables that are being used for regression. And so let's generate some synthetic data, and then we can see principal components regression finding the latent variables using our synthetic data. So first, we're going to make 2 variables, x1 and x2. And these 2 variables are just a pair of random normal variables. They have 100 data points in each vector that we've created with a mean of 0, standard deviation of 1. And now y is exactly a function of x1 and x2. And then we can look at the variables from the underlying data that we're going to create here. So we create A1 through A5. So this is going to be our data set. It's going to be these A10, these 10 A variables. This is going to be what we're going to do regression with. A1 through A5, we've taken X1, and then we've added some noise to X1. So A1 through A5 are all copies of X1 with some noise added. A6 through A10 are all copies of X2 and then with some noise added to those. And so our data frame has A1 through A10, and so we're going to do linear regression, trying to estimate y based on A1 through A10. And so you can think of this as, here's y. Y is actually a function of x1 and x2, and those are our underlying or latent variables. But when we do a regression, we're actually going to do it on A1 through A10, which are 10 variables that are built off of x1 and x2, but with a bunch of noise. So we do principal components regression in R using this command, PCR, and it's in one of the libraries. And so you'll see this in your R lab. So we make our model here, which I've called model PC, and then it's PCR, and then we have to tell it what the data set is, and then some information about scaling and what method for cross-validation. And we do a summary. This is what R tells us back. And so first thing we get is some information about the data that was put in. And then what we care about in this next section, this section tells us the cross-validation. We care about this row, CV, as a function of the number of principal components that are used in our regression. So if we use just the intercept, we of course get bad results. Our cross-validation error is 3.39. One principal component helps a little bit, and then two principal components, and we get 1.630 as our error. And then you can see as we add more principal components, our error goes up a little bit each time. And then out at 10, this is if you did, this is the same as doing linear regression on all 10 variables, our error is up to 1.736. And so we get a 6% decrease in root mean squared error going from linear regression on the full data and then down to linear regression with just the two principal components will give us a 6% decrease in root mean squared error. We can plot root mean squared error as a function of the number of principal components, and we see doing regression on two of the principal components will give us our best result. And so when you use PCA, principal components analysis, with regression, and you say my best result is with, in this example, 2 dimensions, you can think of that as telling you that there's really 2 dimensions worth of useful information in your data. So now we're going to walk through another example of using principal components regression. In this case, we're going to see principal components regression helping us deal with highly correlated variables. And so again, we're going to make up synthetic data, and we know what this data is doing. And then we're going to see principal components analysis, regression, examine the underlying data properly. In this case, allow us to do regression in the presence of a lot of correlated input variables. And so we're going to make this first variable A1, which is a random variable, then A2, which again is a random number variable, and then A3 through A10, which are, if you look at them, each of them is A2 and then plus some noise. So they are all going to be highly correlated to A2. So let's create these random variables. And now we're going to create Y, which is the output that we want to predict. And if you observe the coefficients, it's 3 times A1 plus 2 times A2 and then plus A3. So A2 and A3 are highly correlated as well with each other, as well as A down to A10. Okay, now those were kind of our underlying data. We're going to make X1 through X10, which are each of the A1 through A10s plus some noise, and that's where we're going to build our data frame. And so we do our linear regression model, Y predicted as a function of all those X's, and when we look at the model, down at the bottom, we see the coefficients we get. The coefficient for X1 is 2.88. Remember, the coefficient when we built the data was for A was 3 here. So a good estimate would be exactly 3, and we get 2.88, which is not bad, given that we added some noise. And then the coefficient for X2, when we built the data, this corresponds to A2, and this should be equal to 2, but it's not. It's 0.3. And then X3 should be 1, and it's 0.68. And then X4 should be 0, and X5 should be 0, X6 should be 0, but they're not. You can see those are fluctuating significantly. So our estimates for all of our coefficients, X2 and afterwards, are poor, because we have the large number of correlated variables. We can check the error. The error is 0.329, which isn't particularly good. We can look at the correlation between x1 and x2. The correlation between x1 and x2 is 0.2, and in the plot we can see that they're not very correlated. We can look at the correlation between x1 and x3, and that's 0.2. They're not very correlated. But if we look at x2 and x3, we see they're highly correlated, and we see the plot. And if we looked at any of these later variables like x4 and just pick x7, those would also be correlated. So now we can use PCA regression. That's going to help us improve our regression results in the presence of these correlated input variables. So we use our library. We create our principal components analysis model. And then we look at the summary of the principal components analysis model. And what we see is, looking at the cross-validation row, using one principal component, our data cross-validation here was 2.9, and with 2 it was 0.4136, and 2 principal components is where we get the best results, and then 0.47 on up to 0.49, and then 0.66. So the full regression gives us an error, cross-validation of error of 0.66, in using 2 principal components gives us the best results, cuts our error down by 30%, down to 0.4136. And now we can plot that mean squared error plot. And we can see that our best results occur when we use 2 principal components, and then the error increases as we use more and more principal components up to that 10, that full model. That's the error for using 2 plus 50% above that error amount. So what we observe here are much better results in predictive accuracy when we use principal components, and the improvement comes because we're eliminating a lot of these highly correlated variables. The principal components allows us to do regression and to not be troubled by those highly correlated variables. So review, we've talked about dimension reduction. Dimension reduction is the process of creating a smaller number of regression variables and then doing regression on those regression variables. And so we've talked particularly about PCA regression, where we use the principal components as our regression variables instead of the original input variables. And this improves prediction accuracy in regression when the principal components can capture most of the important information. And that helps when we have a smaller number of underlying dimensions of data, or when we've got highly correlated data. Thank you very much for watching.